Good morning, this is Satish with EasyPower. Today we're going to discuss harmonics analysis in EasyPower, and this is going to be an introductory level webinar, and we'll be covering just the basics. Sometime in the future we'll be looking at advanced options and some case studies that we can present to you. In a power systems, if there are no nonlinear loads, we get a pure sinusoidal wave both for the voltages as well as for the current. So there is a sample of voltage and current waveform, and you can see that it's very smooth. Now, whenever we have nonlinear loads, for example, rectifiers, converters, starting for compensators, and any saturation in the core of magnetic circuits, we get nonlinear output. And for an example, we might be getting something like, for a 6-pulse rectifier, the waveform of the voltage is going to look like this. And you'll see some notching. That is because of the commutation within the rectifiers. And so this is going to affect your performance in the power systems. Some of the other loads that we have, maybe AC, arc furnaces, welders, drives, etc. So this is what the current waveform would look like. Instead of getting a purely sinusoidal waveform, we get a little bit of stepped waveform, and then from the notching you can see the effect on the currents. So what does this look like in the frequency domain? This is a bar chart of the frequency domain plot of the load, the rectifier load. We can see that the first is the fundamental. That's what we want as a perfect waveform. But then we also get other frequencies or other higher harmonics. For example, you get a fifth, and fifth is going to be very strong in the 6-pulse rectifier. So this is the current input that is absorbed by the rectifier circuit. So you'll see a strong, 5th, 7th, 11th, 13th harmonic, etc. And we're going to take a look at what kind of effects they might be having on the rest of the system. For motors and generators, there's going to be conductor losses and heating because of the higher harmonics. There's going to be more iron losses and heating because of that. There might be some mechanical oscillations specifically from the 5th and 7th harmonics. And then there will be additional rotor heating. Any harmonic that's higher than the fundamental is going to go right through into the rotor circuit. For transformers, we will have conductor heating from the current harmonics, and from the voltage harmonics we will get additional iron losses. For cables, skin effect and proximity effect are going to come into play, and it's going to increase the resistance, and therefore there will be more losses and heating in the cables. For capacitors, there might be possible resonant conditions because of the higher harmonics. The main standard we're going to be following is the IEEE 519 standard, and this is the IEEE recommended practices and requirements for harmonics control in electrical power systems. This standard uses some approximations to simplify the circuit and make it easier for us to do the calculations. Now let's take a look at how the resistance changes with the harmonics or the frequency of the current. If you look at this chart here, on the horizontal axis we have the harmonic number, and on the vertical axis we have the ratio, the resistance for that particular harmonic divided by the resistance for the fundamental frequency. So you can see that this is increasing, and the basic equation for skin effect factor is that the resistance is proportional to the square root of the frequency. So that's how it increases. So higher the harmonic, higher the resistance, and therefore the losses are going to be much more prominent. Next, let's take a look at how reactance changes. Now we're talking about two types of reactance. The blue line represents the inductive reactance or the magnetic circuit. And as the frequency increases, the reactance increases proportionately. In the case of capacitors, so this is the red line represents the capacitive reactance. And as the harmonic or the frequency increases, the capacitance increases, and therefore the capacitive reactance decreases. When we model Harmonics source, we have simplified it such that this is represented as a current source injecting the harmonic currents into your system. And whenever we model a harmonic source, for example, rectifiers or VFDs, etc., for the rest of the system, this represents an infinite impedance, meaning you cannot inject any kind of current into the harmonic system. Next, the motors and generators. Motors and generators are treated as sink or shunt impedance, and we model the subtransit impedance there. Loads are treated as sinks, and if you have a resistive load, that is going to cause a little bit of damping of the harmonics there. Utility again is treated as a sink with the Thevenin impedance being modeled. Cables and lines are treated as series impedances. And here's a circuit diagram for that. We treat it as a pipe model, but we use the hyperbolic functions just like in the transmission line. That represents a more accurate model for higher harmonics. For series reactors, transformers, and busways, we just take the resistance and the reactance values as a series impedance. For linear loads and shunt reactors, we treat it as a shunt or a sink. Now, one of the most important values we calculate is the total harmonic distortion. We're looking at the voltage harmonic distortion and the current harmonic distortions. The voltage total harmonic distortion can be represented as the sum of the squares of all the harmonic voltage, and then you take the square root of the sum divided by the fundamental voltage. And it's the same principle for current total harmonic distortion. What we do is we take the square root of the sum of the squares of the individual harmonic currents. Now we're going to take a look at EasyPower and see what kind of reports, what kind of calculations, one-line output, etc. we can run. This is a very simple plant. We've got the utility feeding a transformer, 1000 kVA, and it's feeding a switchgear, and then we've got 3 loads here. The first one on the left is a 400 kilowatt rectifier. So I'm going to take a look at the rectifier data. You just model the load. Then you go into the harmonics tab, and then you have to make sure that this is a harmonic load. Anytime you model it as a linear load, it will be treated just like a resistor and inductor. And in order to model all the harmonic content, we have to enter values here. Now, typically the best practice is you take a meter and take all the measurements and then get the harmonic content entered in the spreadsheet. The first column on the left side is the harmonic number. That is the frequency divided by the fundamental. And the second column represents the harmonic current that you would inject into the system, and this is always shown as a percentage. So if you have any per unit values, remember to multiply it by 100 to get the percentage. And this is the associated angle with respect to the magnitudes of the individual harmonics. Now, if you do not have, let's say, some measurement values and you just want to test out using some typical values, we have a collection of typical values in the library. So what you can do is from the library load, you have different categories. So for this one, it's a rectifier. And there are different types of 6-pulse rectifier values that you can choose. The 6-pulse 0 degrees is basically referring to the transformer that's feeding it, and DD represents 0 degrees phase shift again from the transformer. So these are with respect to what kind of transformer is feeding the rectifier circuit. So if you don't have a specific dedicated transformer feeding the rectifier, just model it as a 6-pulse 0 DD. And you can hit the import button. So when you do that, it's going to populate this spreadsheet. Now, I'm going to click OK to accept this data. Let's take a look at the second type of load on the right side. When I go into the harmonics tab, you can see that this is a linear load. So it could be things like, heater or some kind of inductor circuit. Now, whenever we have a linear type of load, we can specify the resistance factor. And earlier in one of the charts, we showed that the resistance for conductor with the skin effect, what happens is that the resistance increases in proportional to the square root of the frequency. So that square root can be expressed as an exponent here. So that means 0.5 exponent. And so based on the type of load that you have, you can choose what kind of exponent to use that is more suitable for that particular load. So in most cases for conductors, it's going to be 0.5. Next, motors. If this is a direct online motor, then we probably do not need to model any harmonics. So if you look at the harmonics, you'll see that this is linear. Now, in order to model VFDs, what you'll need to do is, first, in the specifications tab, you'll need to check this with adjustable frequency drive. Okay, and then you go to harmonics. So right now, you'll see the load is automatically harmonic. So you can go to industrial and say this is a PWM drive with 100% load. You can choose that and you can import it. So it's going to populate the cells here. Next, let's take a look at transformer dialogue. And we can go to the harmonics tab and specify the model for this. Now you can either choose a resistance factor or you can choose a percentage CF. And so a typical value for percentage CF would be 15%, and that accounts for the eddy current losses. If you look at the REXP, a typical value earlier we said for simple conductors might be 0.5 to account for skin effect, and if we keep on adding the other effects like proximity effects and core losses in the transformer core, because of the harmonics, then a typical value for that might be close to 0.7 as the exponent. So let's model it as that. And we can do something similar for conductors. Conductors to have a harmonics tab where you can choose the resistance factor. Now you can see that this is already 0.5, which accounts for the skin effect. Finally, let's take a look at the utility. There are two types of model for utility. One is modeling as a simple Thevenin circuit. So this is treated as a resistance and a reactance. And the reactance would have, impedance values directly proportional to the frequency, whereas the resistance would be proportional to the square root of the frequency, as shown by this resistance factor here. The other option is to use table values. So when we click on table values, what we're saying is utility has specified a frequency response for the grid. And so for different harmonic numbers, you can have different positive sequence and zero sequence impedances. So this is something you'll have to obtain from the utility company itself. So for a simple analysis, we'll just go with the short circuit values or the Thevenin impedance. Okay, now let's start looking at what kind of calculations we can do with harmonics. Click on the harmonics icon on your ribbon and your toolbar changes. The first thing we're going to look at is the total harmonics distortion. To calculate that, click on the summation button on the very left side and you'll see some values appear. So let's take a look here. We can see that the harmonic distortion on the voltage is 10.6% and on the current is 30%. So in typical practice, we would like to limit the voltage distortion to something like 5% or less. Now, in order to see different kind of calculations, we can choose some of these buttons, and these are all specified in the IEEE 519 standard. So the first thing we're displaying is VTHD and ITHD. Okay, any branch would show, a branch would be things like cables, transformers, etc., or even busways. They would show the current. The voltage always is shown on the buses at a diagonal like this. Now, there are other values like VRSS, that is root sum of squares, and same principle for currents. And we can also do VSUM. VSUM is a theoretical or hypothetical maximum possible voltage you might get if all the harmonic voltages, all the magnitudes, had the same phase angle. So what we're doing is just adding up the magnitudes. So that's just a hypothetical value. It's rarely possible to get that exact same phase alignment for voltages. Then we have the telephone interference factors here, IT product and VT products. We can also take a look at transformer derating. So this transformer would need to be derated by 78% because of the higher harmonics that we have. Conductor derating. So you can display the conductor derating here. Transformer K factor. So this transformer, when you purchase a transformer that's suitable for this kind of load, it'll need to have a K factor of at least 3.1% or higher. Now, we already said there are lots of losses in the system because of harmonics. To calculate all the losses from the different harmonics, we get you click on this button and you can see how much of additional losses. Now let's compare that with just the fundamental loss. To look at the fundamental loss, you would have to go to Power Flow, Run Solve, and look at the losses here. See, 4.9 is what you would get as the losses, 4.9 kilowatts that is, but in Harmonics, you'd get 6.6. So higher losses and more heating, so you can get damage from higher heating. Okay, so those are some of the one-line results. Now let's take a look at what kind of reports we can generate. Click on the Harmonics report, and you'll get this Harmonics options dialog with the text output. Let's look at summation detailed report. Check this box, click OK, and we go to Window and choose the summation detailed report. So for every bus and for every branch within that bus, we get a report of ITHT values, and for every bus we get the THT values. And you can also look at RSS and TIF values there in the vSub. Next, we're going to take a look at current injection. Now, if I were to do some investigation and I needed to know if I inject a certain harmonic frequency at a certain bus, what kind of a response am I going to get from that? To do that, I would select the bus first. When you select the bus, it turns green. And then you would click on single point current flow. So you're injecting the current into that bus. And when you do that, you get the response of the system. Now the question is, how do we control what kind of currents you're injecting into that bus? So click on Harmonics options and go to Control. And in the Control tab, you'll see this Scan Single Point Injection. So for this single point injection, we're doing an injection of 1 per unit current, which is going to be pretty large. So that's a 1 per unit on a system base. Let's say you want to set it to amps and you wanted to inject just 100 amps of a harmonic current. So the question is, what kind of harmonic number are you injecting here? By default, it's going to be 5th harmonic. So if you want to change that to a certain different harmonic number, you can do that. But we are injecting 1 harmonic number at a time. So 100 amps of 5th harmonic, click OK, and you get your response there. So based on that 5th harmonic injection, on bus 2, which is the switchgear, you would have 0.028 kV or 28 volts. That's going to be impressed on the bus. Now, if you have multiple sources in your system and you wanted to perform all point current injection, you can do that. All source current flow. Click on that, and each of these sources would inject at their respective buses, and you can see the response for the 5th harmonic there. Similar to the one-line results for current injection, we can also generate reports here. In the text output tab, we have a current flow report. So check this box, current flow report, and click OK. And go to Window, and you can see your current flow report. And you can see what kind of voltages occur at the buses, and the branch currents that will be flowing because of the current injection that you just did. Next, we'll take a look at bar charts. Bar charts can be created for either bus voltages or branch currents. So let's take a look at, I'm going to do a summation first and select this branch or this cable and see what kind of current distribution we have for different harmonics levels. So click on the bar chart icon on your ribbon after selecting your branch, and this is what you would get. So the first bar is the fundamental frequency, and then this is the fifth, followed by 7th, 11th, 13th, etc. And right now on this horizontal scale we have the different harmonic numbers, and it goes up to 21. If you're interested in seeing higher harmonic numbers, what you'd need to do is go back to the harmonics options and then go to plot output. So by default the software has up to 21st harmonic. So let's say you want to see up to 50th harmonic. So I would type in 50 in the summation bar chart range, starting at 0. Step 1. Click OK. Select your cable and click on bar chart. So now you can see up to 50th harmonic. And for this vertical axis right now it's in amps magnitude, and if you want to see in different values you can do that. So to do that, go to harmonics and plot output. Here you'll see that the branch current output is in amps. So if you want to see in per unit system base or per unit power flow base, you can choose those values too. Next, let's take a look at the distribution of voltage. Select the bus and then click on the bar chart. So that's how the bar chart looks for different frequencies, the voltage on bus. Next thing we're going to take a look at is frequency scan. Now, whenever you double click on a bus, you can get a frequency scan or something like a Bode plot, or you can just select the bus and click on scan. So let me do that. I select the bus, click on scan. So this is pretty much a frequency response of the system. And since right now the circuit is mostly inductive and there's very little capacitance in the cables, we see a pretty much linear response. So as the frequency increases, the impedance increases. Going back into THD calculations, let's take a look at THD values here. We see that this is slightly high because of the harmonics generated from these loads. So we probably want to reduce the harmonic content by adding a filter here. So what we're going to do is go back to database edit focus, and I'm going to insert a filter. To insert a filter, click on this filter icon from the equipment palette and connect it to one of the breakers there. Now I'm going to enter some data that might be suitable for this filter. So that's the resistance part of this inductor. You can see the notch filter here. We have different types of filters, first order, second order, third order. For now, just for simplicity, I'm going to choose a notch filter there. So it's got an impedance of 0.03 ohms reactance. And say this is a 300 kVAR capacitor in the filter, so that will be 0.3 megavars. at 0.48 kV. So that's what my filter looks like. Click OK. Now I go into Harmonics Focus and I do a frequency scan on this bus. Now what you'll see is the frequency response of the system has changed because of the filter. The filter allows a lot of the currents to be absorbed by itself on the fifth harmonic. Now if you look at, let me close this down and do a summation here. You'll see that it's generating fifth harmonic a fairly significant value. So what we're trying to do with the filter is create a very low pass or create a low impedance path for the fifth harmonic there. So when we do a frequency scan, we're getting a very low impedance there at the fifth harmonic. So with the filter, we also get a parallel resonance, a little higher than the third harmonic. It might be close to fourth harmonic too. And that's a typical response of a filter connected with the system. So the question is, after adding this filter, what have we done to the total harmonic distortion? Let's run a summation again, and you'll see that now this has dropped down to 5.3. Earlier, without the filter, if you want to check what the filter effects are, you can just toggle this breaker. So double click on this breaker, it's going to open it. So without the filter, it's going to be 10.68. With the filter, it's going to be 5.36. So you have reduced the harmonic distortion in your system by adding the filter. Let's take a look at some of the other reports that you can generate. The first one we're going to take a look at is IEEE 519 report. So anytime you generate a report, make sure you hit the summation button so that it refreshes your report there. Okay, so Okay, now in order to generate a 519 report, the first thing you have to do is define a point of common coupling. So point of common couplings are defined in circuit breakers in EasyPower. That's just a convention that we use. So double click on either high voltage breaker if there is in your system, or a low voltage breaker. Double click and you can go to Harmonics and check this box, monitor IEEE 519 point of common coupling. So this is where you would measure and verify that your harmonic is at an acceptable level. So there are two fields that you need to enter at the circuit breaker, the kVA demand. So this would be pretty much for your last 12 months, what is the peak demand like? So let's say that was 1000 kVA. And the second value is a ratio. What is the ratio of short circuit current to the load? So if you have a 5% impedance, your ratio is going to be something like 20 by 1. So I'll go for something like 18. That's the ratio here. Now go into Harmonics. When you run the summation, go to Window and Harmonic Summation Summary Report. There you'll see the IEEE 519 report at the point of common coupling BL1. That is the breaker. So the IEEE 519 report is slightly different. What it does is it groups different harmonics into bins. For example, anything less than 11 is sorted into one bin. Then we've got 11 to 16, etc. So different harmonic numbers, different groups. And so we calculate odd harmonics and even harmonics and look at the IEEE limits. So anytime you exceed the IEEE limits, we flag it with a red color. So after we add the filter, we still have exceeded the IEEE limits for VTHD. So that means we probably need to have a slightly larger filter there. Next, we'll take a look at other types of reports. I'm going to combine a whole lot of tables into the same report. Okay, so this is the harmonic summation summary report, and we can take a look at different values tabulated. The first one is the summation results, so we're looking primarily interested at the THD values, and then we have the other three values tabulated for bus voltages. Then we have the branch currents. A branch would be any cable, transformer, etc., or even loads and motors. Then we can take a look at losses, how much of losses exist because of the various harmonic contents. Transformer derating report. And so you'll see that there's some improvement. Earlier the derating was significant. Now with the filter, it's a lot improved. Conductor derating report there, and filter summary report. So this is showing what the RMS value is that the filter is absorbing and the losses in the filter, etc. Now let's take a look at the control tab. Whenever we run harmonics analysis, it's always good to have power flow. And the reason we need to have power flow included in our analysis is because the fundamental calculations are most accurate when we have power flow running. Now, if you do not have the power flow calculation tool, what you will need to do is base it on equipment rating. So let's go back into database edit focus. Harmonics. So we have the choice of equipment rating and user specified values so that it takes a certain percentage when it calculates these values. Now in terms of looking at power flow results, what's going to happen is you can, if you do not have the power flow, then all the percentage that you calculate is based on a certain user specified value that you get. So always make sure that to get better results, use power flow for summation calculations. You're all probably familiar with neutral currents and third harmonics or triplets. And whenever you've got a three-phase load with neutral current carrying third harmonic or triplets, they tend to triple and add a lot of third harmonic or the triplet in the neutral circuit. And in order to calculate the effect of that, you can choose to use positive sequence networks with zero sequence triplets. So anytime you have third harmonics in your systems, make sure that you choose this choice so that the zero sequence is accounted for the neutral path. And summation thresholds, anytime you want to get a warning on the one line drawing, then what you can do is specify these. Anytime these limits are exceeded, they'll be flagged red. Now, earlier in the frequency plot, we looked at just the per unit impedance. If we want, we can also show different values like X value, resistance value, values in ohms, or the per unit voltages. Or you can also have a plot separately for degrees. For currents, you can either express it as per unit current or amps. Same thing for bar chart. You can do voltages, different kinds of voltages there, and amps or system base versus calculated for power flow. So that was a quick overview of harmonics in EasyPower. And in the future, we'll be having an advanced webinar on harmonics analysis. Thank you very much and have a good day.